Welcome to our next virtual lab together. However, in this video, we're going to be doing 3 virtual labs at the same time. Yeah, I said that right. 3 of them. So part of this lab experiment is for you to kind of watch the laboratory video, make sure that you take good notes, because folks, we're going to be doing 3 experiments at the same time. The reason is because these 3 lab experiments are basically the same procedure. It's just using a different starting material in order to do it. So instead of making 3 separate videos about an hour apiece for you to watch, I just decided to put all 3 of them together into one lump sum video, as long as you take the proper notes and separate the 3 starting reagents from each other. All right, so this experiment is going to focus on benzene directors. So in lecture, we've talked about benzene. We've talked about the groups on benzene that says, I'm going to tell you where to go. And we talked about activators and we talked about deactivators. Well, in this lab, it's going to prove whether or not something is an activator or deactivator, and then for us to kind of figure out or predict OMP, Becky, directors. So, without wasting any more time, we're going to be doing 3 different starting reagents here. So, in one set of lab data, I'm going to have something called methyl p-Hydroxybenzoate. Now, I'm not going to draw the structure for you folks because that's part of this lab. You're going to have to draw the structure of methyl p-Hydroxybenzoate in order to determine what type of product's going to form. And if you don't know the structure, Google it. However, the name tells you everything that you should know. So on a test, methyl p-Hydroxybenzoate, you should be able to draw that structure without any outside help. All right, so this is from MP. That is the manufacturer of this chemical, and the lot number is Q7915. So there's my component, a component for one set of laboratory data. The next component, I'm going to be using acetanilide. Now, this is a very, very old bottle. It's older than me. It was probably ordered back into the 60s or the 70s, and most of the time this comes with an E at the end of the name. So acetanilide, that probably doesn't give you an insight of what's on this structure as far as the benzene ring is concerned. So this one you probably do have to Google at a certain point in time, or Wikipedia. Go ahead and use that. It's okay. No one says that you can't. No one says that they're going to scream at you if you do. So acetanilide is going to be our next structure. And then, and by the way, folks, this is like an old paint can. It's got a metal lid and everything, just like a paint can does. Things don't come that way anymore. All right, and then the next one is methyl benzoate. All right, so there's methyl benzoate. It is a liquid. The other 2 are solids. So methyl benzoate comes from alpha ASAR, and the lot number here is L04144. Or, sorry, that's a stock number. The lot number here is 10, that's a smudge, but that also says 0, 40380. All right, so there's methyl benzoate, manufacturer and lot number. Mallincroft is the acetanilide manufacturer, and this lot number, WSMY. Again, that shows you how old. If it's old enough to only have 4 letters as a stock number or a lot number, then we know it's old. All right, so these are the 3 components I'm going to be using, folks. Methyl p-Hydroxybenzoate, acetanilide, and methyl benzoate. All right, now if I go through the lab directions, and I'm going to pull up the lab document, we're going to kind of follow through here a little bit together. And it says number 1, okay, place equal volumes of ice and tap water in a 400 ml beaker so that the beaker is 75% full, and then prepared this chilled water for part 3 and 4 by pouring approximately 30 mils of distilled or deionized water into a 125 ml Erlenmeyer flask and placed the flask in an ice water bath. Blah, 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 blah. All that basically told me is make an ice water bath, and that's exactly what I did here. All right, so I went to the freezer, took out some ice cubes. That's all it requires. Add some water to it, and away we go. Now, the reason the ice bath is going to be important is because we have to chill things down appropriately. So, in the directions, it says, caution, nitric and sulfuric acid are toxic and oxidizing. They can cause severe burns. Label 2 test tubes, one that says nitric and one that says sulfuric. Transfer a ½ ml of nitric, transfer 0.6 mils of sulfuric, and chill both of the test tubes in the ice water bath for 15 minutes. All right, so there's my ice water bath, which means that I also need to go to our cabinet and I need to get our concentrated nitric and our concentrated sulfuric from the lab drawers. All right, now the lab cabinets. So here's our concentrated acid jars. We do not keep our concentrated acids in the regular huge 2 or 4 liter jugs. This is just way too big. If someone breaks a 2 liter or 4 liter jug, folks, where do you think it's going to go? It's going to go all on the floor, and I don't want it all on the floor because I don't want to clean it up. So we pour these in smaller containers for you to use. So the one to the right-hand side, you're going to see conch right up here at the top, nitric acid, and the one to the left, you're going to see conch, sulfuric acid. These are concentrated. They do burn. They eat metals. I can dissolve a penny very easily with nitric. I can dissolve your clothing and your shoes very easily with sulfuric. And if they get on you for any long period of time, they are going to start to burn and they're going to start to eat your skin. So we got to be careful with them when we handle them. All right, so those lab directions told me to put a ½ ml, 0.5, and then 0.6 mils of the other acid into a test tube and to cool it. All right, so the way that I'm going to do this, I'm going to use a micro pipetter. I'm not going to use a glass pipette. I'm not going to use graduated cylinders. They're skanky. They don't really give me the total volume as proper as a volumetric pipette does. But this micro pipetter puts a little bit of automation to it. So I've taken this micro pipetter that's 100 to 1,000 microliters, which basically means 0.1 to 1 milliliters. And I've dialed this in to 0.50. Well, for this micropipetter, it's a little weird. The 4th number actually comes from that tick mark, so this is another 0. So this is 500, which is 500 microliters, and 500 microliters is equal to 0.5 mils. So I'm going to take the micropipetter, dial it in to 0.50, and I'm going to put it into the sulfuric acid. All right, so there's my my nitric acid. Sorry, this is not sulfuric. This is nitric. Look at that. It tells me right on the bottle that it's nitric. So let's make that change. There we go. And then I'm going to suck up very slowly the nitric acid into my micropipetter, and I will dispense it into a set of 3 test tubes. So test tube number 1, number 2, number 3, nitric, nitric, nitric. Again, remember, I told you that we're going to be doing this 3 separate times. And this one video is for 3 separate labs. Okay, so there's the addition of the nitric. Now I'm going to go back to my micropipetter, and this time I dial it into 0.60, which basically means 600. And 600 microliters is equal to 0.6 milliliters. Do the conversion if you don't believe me. I promise it's true. All right, so in the other 3 test tubes, I'm going to put sulfuric, sulfuric, and sulfuric on the inside. So now I have 3 sets. Nitric sulfuric, nitric sulfuric, and nitric and sulfuric. Folks, do you see what we're doing here? Think about the benzene reactions that we've done. And the benzene reaction that we are focused on in this experiment is the addition of nitric acid with sulfuric acid written above the arrow. That is the reaction that we are doing, which means that this is nitration. We're going to be taking these benzene rings that we're using in the lab together, and we're going to be nitrating them, which means an NO2 group is going to go on to the ring of these structures that I am using in the very beginning. All right, now, the directions told me to take these tubes and get the acids really, really cold. And that's what I did. So I grabbed my test tubes up together. I labeled them so I know which one was which. I put a rubber band against them to keep them together. And then I put them into that ice water bath. 10:34 to 10:56 that morning. And now I need to turn to my benzene reagents. What are we going to be using? All right. Well, the very first one that I decided to weigh out or to use was acetanilide. This is what acetanilide looks like. In case you need the observations, hint, hint, a data sheet might ask for them. Here is acetanilide. All right, so it's very fluffy, it's white, it's powdery, it doesn't really have an odor or a smell to it at all. And I need to weigh out a certain amount. Okay, well, how much? Well, the directions are going to tell me. All right, so step number 3 says place 0.5 grams of acetanilide into a flask and then add 1 milliliter of concentrated sulfuric acid. Okay, well, that's not a problem. So I'm going to go to my balance. I'm going to zero it out with the weigh boat. And then I'm going to add acetanilide to it until I get the proper amount. And my balance here is giving me 527.5 milligrams. That's the way that the balance decided to give me the number. So that's what I wrote down. I could have changed that to a gram if I wanted to. That's not a problem. But folks, you should be able to do that conversion in your head. Milli to a gram, that's 3 zeros. Move a decimal 3 times. That's all that you need. All right, so there's my reagent number 1. All right, so reagent number 2, methyl p-Hydroxybenzoate. And there it is. Methyl p-Hydroxybenzoate. Very similar to acetanilide as far as observations go. The difference is that this is more salt texture. It's more grainy. The acetanilide was a little fluffy, and this one's a little granular instead. All right, so once again, I go to my balance, I tear it out, and then I add my methyl p-Hydroxybenzoate into the weigh boat, and I get 604.6 milligrams. And finally, the last one that we're going to be doing together, I told you we're going to do 3, is methyl benzoate. Just pure methyl benzoate. This one doesn't have a hydroxy with it. So methyl benzoate. Methyl benzoate was the weird one. Methyl benzoate was the liquid in the brown bottle. So I had to suck this stuff up using a plastic pipetter. So with this one, I do need an Erlenmeyer flask right off the get-go. So I'm just going to use this as my weigh boat. It's going to be suitable enough. It makes it very easy to transfer because I don't have to transfer anything. So here is my little bitty tiny weeny 25 milliliter Erlenmeyer flask. So I'm going to put that onto my balance. I'm going to tear it out. And I did. I promise I don't have a picture, but I did. And then I'm going to add methyl benzoate to that Erlenmeyer flask. Well, be careful, because I did finally switch the unit here, and this is 0.5494 grams of methyl benzoate that I have used for this experiment. All right, so there are the 3 preps for the 3 different labs that you'll be submitting to me over the course of a couple of weeks. acetanilide, methyl p-Hydroxybenzoate, and then regular methyl benzoate. All right, so there we go, folks. There it is. So reagent number 3, if I want to give you a better picture of it, this is about as good as I can get. It was a very clear liquid. It did have an odor, and it smelled like one of those kind of chemical residue remover type of solvents that you would get at Walmart or Lowe's or Home Depot or another big box store. So there is reagent number 3 with my methyl. All right, so what I have here is a video, and it's just me adding the acids together at this step. If I go back to the directions, it's then going to say, okay, now that you have cooled these acids together, you need to mix the nitric and the sulfuric into one test tube, because you're eventually going to add that at the same time into these reagents. All right, so that's what I'm going to do. Use a Pasteur pipette. Very slowly add the cold sulfuric acid dropwise to the cold nitric acid. Swirl it every 3 or 4 drops or so, and then after you add all of the sulfuric, allow it to stand in the ice bath for another 10 minutes. All right, so not a problem. That's pretty easy to do. I think I've got this. So here's a video of me just adding the acids together. All right, folks, I really don't know what you saw here because I had a glitch on my end recording this video, and I don't want to stop at 16 minutes into it just to figure it out. So just in case that you didn't get any of that, I'm going to replay this one more time. This is me sucking out one acid, putting it into the test tube of the other, and mixing these two things together to give me what we call the nitrating solution. Again, very difficult process on my end. You would not imagine the trouble that I had to go through to do this horrible, very complicated lab experiment. So we mix the two acids together. I do this 2 more times because we've got 2 other methods and labs that we're doing. So I'm just doing 3, and we'll just do it in one fell swoop. So that way we can take care of all 3 of these labs in one video. So they like for you to keep this cold because it does generate quite a bit of heat. You know, anytime acids, especially nitric and sulfuric, are used with some water or in basically organic reactions, you're going to start to see a lot of evolution of heat, a lot of steam that can be generated and so forth. So that's why they told us to keep it cold. It's still cold to the touch, and it did not warm up when I added these 2 things together, at least not substantial enough for me to notice it. All right, so back into the ice bath they go. This time it's 11:04, and all 3 are going inside of that beaker. All right, now I need to keep following the directions, right? So now after this point, if I go back and I take a look at the directions, it's going to say, take these solids that you are using, or in the case of methyl benzoate, a liquid, and you're going to add 1 ml of sulfuric acid to that. All right, so that's going to be my next step. I'm going to add sulfuric acid to each one of these 3 components for each one of these labs that we're going to be doing. So the first one here is adding sulfuric to acetanilide. Common trick in a lab, your weigh boats, fold them in half, give you a nice little spout to knock all of your solids down into. It's one of the reasons they're made that way instead of a flat little square or a circle. Hello? Somebody answer that phone, please. And here goes the sulfuric acid addition. All right, guys. So as you can expect, the data sheet probably asks for observations. This is your observations of adding sulfuric to the acetanilide. This is not our nitrating. This is just adding sulfuric to hopefully dissolve this stuff up. So after I added the sulfuric to that, it didn't fully dissolve. This is what I ended up with. And before I go on to the next step, I do want it to dissolve on me. So this is not very good enough. I'm not really happy with this, but I'm going to move on to our second. And our second is adding sulfuric to our methyl p-Hydroxybenzoate. So here is component number 2. Once again, fold the weigh boat, dump that stuff in there, and we're going to add 1 ml of sulfuric acid to the flask. Pay attention to the observations. It's probably going to ask them on the data sheet. So that was the addition of the sulfuric, and I'm getting ready to swish. And there you go. Did it dissolve? I don't think so. Okay, so the close-up picture of that one, folks, this is what we've got. Again, I'm not very happy. It didn't fully dissolve. The lab directions tell me make sure it dissolves before we go further. And then here is our final one, which is adding sulfuric acid to methyl benzoate. Now, keep in mind, methyl benzoate was already a liquid. There it is. It's already a liquid. I didn't have to worry about a solid with this one. And I'm getting ready to add sulfuric acid to it. So let's see if this looks any different. Well, that was kind of boring. No one said that organic lab was very exciting every single time. So I didn't really see anything happen. It just mixed together. It's still clear. It didn't change colors. It didn't really produce steam. It didn't produce a precipitate or nothing. So once again, here is a close-up picture of what that looked like with the addition of sulfuric. So I wasn't very happy with any of these folks. I wasn't happy with any of them. So because I wanted it to dissolve, I put all 3 of these on a hot plate on a very gentle heat setting. And I just slowly warmed them up. And by warming them up, what I'm hoping to do is dissolve these crystals for you. So that way we can ensure the reaction is going to go forward like we want it to. Because I need them to dissolve up. And they're chunky, if they're crystalline, in the flask, it's not going to work for me. All right, so there's the settings for the hot plate. Again, very, very low. So I'll leave them on there for like 5 or so minutes. It doesn't take a long amount of time at all. And I take them off the hot plate. And folks, this is what we end up with now. So I think by showing you this video, we feel a little bit better about the reaction after this. So they are going to be dissolved. I can see them. No crystals around in that solution. Bye-bye, crystal. We can go on to the next one. Once again, make your observations as you need. All right, so the one to the left is component 1. That is the acetanilide. The component in the middle is number 2. That is the methyl hydroxy, blah, blah, blah. And then number 3 is going to be just the methyl benzoate. Simple and clean, right? All right, so the next one is another video because at this point it's going to tell me to cool it. All right, so it says, let's read together. Clamp the flask containing the mixture to a support stand. Lower the flask in an ice water bath for 5 minutes. Use a Pasteur pipette. Slowly add the nitrating solution in the test tube to the Erlenmeyer flask containing your compound. And then after you add the nitrating solution, You allow the mixture to stand for 30 to 45 minutes. All right, so I'm cooling it to room temperature here at this point. It did generate a little bit of heat on me after I dissolved it. So I just want to make sure that everything is at room temperature before I go forward. So on the hot plate, they've dissolved. I've taken them off. I've let them cool to room temp before I go on to that next step that we just read together. So here the time is 11:24. There's my nitrating solutions right in there. And those nitrating solutions, there's my beaker of ice water. That's good. That's what I want to see. And I'm getting ready to add the nitrating solution to my first one, which is acetanilide. So let's take a look, see what's going to happen. So you can see my test tubes of nitrating solution on the back. I'm going to suck all of that solution up. There's a close-up view of that Erlenmeyer flask, and I'm going to slowly add the nitrating to it. Make your observations. So exciting. Oh, look at those observations. Oh, wait a minute. What just happened? And there's your observation for nitrating solution number 1. It keeps going. A beautiful honey amber color. All right, so there's nitrating solution number 1. That happened at 11:27 that morning. And then I'm going to do the same thing for the other 2. So here is the second lab document that you'll be working on. This is adding nitrating solution to the methyl hydroxy blah, 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 blah. And this is at 11:31 that morning. Let's see if it does anything different. So that's original, starting out before the nitrating solution is added. And now in the background, you can see me get up the nitric. And we're going to slowly add it together. Observations. And there we go. Look at that. Total difference. You can even hear the sizzle of the steam that's coming off of that flask. It is warm on the bottom. And look, do you see the brown vapor that's pouring out of the Erlenmeyer? Oh, that's bad stuff. That's nitrous fumes right there. Look at all of that brownish liquid coming out of there. So observations for this one was totally different than the first one, which was okay because, folks, this is a completely different compound. All right, and then finally, I'll go to adding the nitrating solution to number 3. This was my liquid methyl benzoate that we started with in the very beginning. All right, so there's my methyl benzoate in the flask, and I'm getting ready to add the nitrating solution to it. So, again, pay attention, write down some observations. They're probably going to be asked on the sheet, and let's see what happens together. And there you go. So not as exciting as the first 2, but we can at least report a change. We can see something different now than what it was in the beginning. So you can make those notes down as you want. Notice my fingers. It is generating quite a bit of heat at the very bottom. So in the ice bath it goes. And now, folks, I just need to wait. I need to wait on these 3. This happened at 11:34 that morning. So I need to now go to the next step, and I need to figure out what I need to do. All right, so in the directions, after I add the nitrating solution to the test tube, after you add all the nitrating solution, allow the mixture to stand in the ice water bath for 30 to 45 minutes, swirling every 5 minutes. And then after that time period, we're going to add water. All right, so here at 12:34 that morning, a little more than an hour, which is okay. It told me 30, 45 minutes. I overshot it a little bit, but it's okay. I mean, I was in the lab, I was having fun. So when you're having fun, time flies by, right? So here's video number 1, and we're going to add water. So this is the Acetanilide nitrating product that is now in this flask. So now we're going to add water, and the purpose of adding water is to really push out my new product that is hopefully formed. So let's see what happens when we add water to this solution. It tells me 10 mils. Here you see the graduated cylinder over on the right hand side. I'm going to fill this up to 10. It doesn't have to be perfect, folks. I just need it to precipitate out if that's what it's going to do. So let's take a look together. Let's record those observations down because, again, you know they're going to be asked. So Acetanilide product right here. That is what I ended up with. And now we're getting ready to add water. What happens? And there you go. I think it's very obvious on what kind of observational changes that you could make. Notice these colors, they're all orange and reddish and brown and burnt. This is pretty normal for nitrating reactions. As an undergraduate, I did a couple of nitrating reactions, and folks, everything that I touched ended up being brown, orange, reddish, yellow. Everything. My notebook, my textbook, my pencils, the stuff in my backpack, everything that I was touching ended up turning that color. And not just for that day, but it seemed like it happened all semester long. I was cursed with nitration reactions. All right, so here's video number 2. We're going to add water to it as well. This one's going to happen at 12:37 in the afternoon. And this is the methyl hydroxy blah, blah, blah. All right, so here we go. 10 more mils of water added to the side. And I'm going to add that water to that nitrating product right there. So there is the final look at what this stuff looks like before I add the water. A lot of sludge, a lot of crystal there at the very bottom. Completely different color than the first one. And here goes the water. And what did I tell you? What color is it? Look at there. Well, who would have thought? At least you've learned anything from the class. Nitrating is going to be brown-orange. And another close-up so you can make observations. All right, so in the bath it goes. We need to let it sit for a few more minutes. And then I'm going to go on to component number 3, which is our third lab together. And this is methyl benzoate. So I'm going to add water to the methyl benzoate. This happened at 12:41 p.m. in the afternoon. Once again, there's my graduated cylinder. I need 10 mils of water. We're going to take it out of this ice bath together. And we're going to add water to that reagent. Make observations. It'll probably show up on the data sheet. I sound like a broken record. That, of course, started completely different. Did you see that? The other two, maybe not so much, but this one was pretty much a solid already. And in goes the water. And there I was trying to break up the solid chunk. I really don't like it when that happens, especially with the addition of the water. So I'm going to end up taking a stirring rod or a plastic pipetter, and I'm just going to kind of stir that up a little bit, just so I can break up that solid chunk. I really don't like to see that. So water water, water is going to rinse, 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 and push out product. But this product was already pushed out, so half of this job was already done. And I sucked some of it up in the pipette, so this extra little bit of water is just to rinse out everything on the inside of that plastic pipetter. I want recovery. I want to recapture as much as I can and recover as much as I can in the procedure, so that's why I did that. All right, so here's a picture of all three of these now that have added water. The very first one is the acetanilide. The middle one is the methyl p-Hydroxybenzoate. And the third one is just the methyl benzoate. So those are the three labs that you'll be turning in, 1 and 2 and 3. And that's the order that you're seeing them. All right, so there's your observations of what happens after the water. And now what we need to do is we need to filter. So after we let this set, okay, it says allow the mixture to stand in the ice water bath for 30-45 minutes, and we did. Add water, and then allow it to stand for another 5 to 10 minutes, and we did, to complete the crystal formation. And then it's going to say filter. Filter the reaction mixer using a vacuum filtration. All right, so that's easy enough. Again, no one says it's got to be complicated. So here is basically the product of number 1. That is what that looks like, 12:57 p.m. Here's the product of number 2 after it stood and sat. That time is 12:57 p.m. And here is product number 3. And again, that time is 12:57. So we now need to filter. You now know what these look like after the reaction period, after the addition of water. And now we're going to filter these things one by one. So here's the vacuum aspirator. Back here in the back is my faucet. That faucet is connected to a hose that's on the filter flask that's right here. The Buckner funnel is going to sit on top. I'm going to put a piece of filter paper into the Buckner funnel. I'm going to turn the aspirator on. And we're going to filter our products together. All right. So there's the filter paper. Grade number 1 Wattman is what we decided to use. It fits the Buckner funnel perfectly. So in it goes. Then I'm going to pre-wet the filter paper to do what we call seat the filter paper. That way it stops up all of the holes in the Buckner funnel. That's me checking to make sure I've got suction, and I do. And now we're going to pour through. Acetanilide is going to be the first. And there it goes, folks. There it goes. Down the hatch. Notice the crystals that are left behind. Again, I want all of those transferred out. So I'm going to keep transferring it over and over as much as I can. I want to recover all of those crystals for reporting procedures. Not reporting. What's reporting procedures? Who knows? The data sheet is probably going to ask you observations on the crystal as well as the liquid that's below in the filter flask. So just try to make an observation of this as you begin to watch these videos for the filtration of each one. Okay, so what you did not see there is I stopped the video early. I still had crystal residue that was left here in the flask, and I just spent an extra few minutes just rinsing that flask out as much as I could. Here is an observation of the crystals that were on top in the filter paper, so that way you can make an observation of what we would call the crude product from the acetanilide nitration reaction. All right, so that's what those crystals look like. So not only am I showing you the crystals up here at the top, but I'm also going to end up showing you the filtrate, which is the liquid that sits down below. So that is the observation of the filtrate. I don't want to see any crystals down there because that means I did not filter it the proper way. I want something very clear that I can see through, that has no crystal at all or extra precipitation that's there. All right, so there's the filtration of step number 1. Well, I'm going to do the same thing to number 2, folks. I mean, there's no difference here. It's all the same procedure. It's all the same step. So here is, and I'm going to turn that off so that way you don't have to hear it. But there's the aspirator, and that aspirator is going to get a piece of filter paper just like the first one did. That filter paper is going to go in. I pre-wet it. That seats the filter paper onto the holes. Make sure they're all covered. And then this is product number 2. So this is from the Methyl p-Hydroxy benzoate right there. All right. So we're going to dump that through just like we did the first. It's going to be better if you dump it all at once in the very beginning because we have very little crystal. Allow that to pour through and then give your flask a couple of rinses with some DI water. This one rinsed out much better. Okay, now that doesn't mean that it's a better product. It just means that it didn't stick to the sides of the flask like the first one did. So as you can already tell, these rinse steps are more efficient in getting rid of those crystals out of that flask. So I'm going to work with this just for a little bit, and then we'll move on and we'll take a look at the final observation of the crystal and of the filtrate from the filtration step. So what I'm looking for there is the DI wash. I noticed that there was a tinge of color in the DI wash, and every time that I would rinse that flask out, I wanted to make sure that there was no color. If there was color, then that means I was still removing stuff from the flask. So that's why I keep looking at the flask, and I keep putting my hand behind it, because I wanted that water wash to be just like water. I didn't want a yellow or a reddish or an orangey color that was associated with it. All right, so here's the observations for product number 2. So there's what the crude looks like, and there is the filtrate, and that's what that looks like. So some of the yellow came out of both of these, right? However, each one of these crystals still had some yellowish tinge to it. So that is something that we probably want to make a note of in the observations as well. All right, so here's filtration number 3, and filtration number 3 is the methyl benzoate. So again, I go back, turn on the aspirator. Once more, another piece of filter paper goes into the vector funnel, pre-wet, seat the filter paper, make sure all the holes are stopped up. And we do all of that before we filter it. Okay, so there's my product. That looks different than the first 2 already, right? And I'm going to swish and dump. And then rinse, rinse, rinse. until I get most of that product out of there. Notice again, folks, that this flask, it's already pretty clear, and there's no really color left in there at all. I'm just trying to loosen up some of the stuck crystals on the sides in order to transfer them over. That's the only thing that I'm doing here in this step. Okay, so there's the filtration of product number 3. As with the other two, I'm going to give you a short video on the crystals of what they look like in the Buckner funnel. So here is the crystal from step number 3, and then there's the filtrate as well from that filtration step. So you can still see a slight tinge of yellowish. I mean, almost urine color. I hate to say that, but it's almost like urine color in the flask. Well, if you're hydrated enough, it's urine color. If you're not hydrated, then it's going to be brown and nasty, like the very first 1 or 2 steps of the lab. All right, so here's another video that I've taken for your observational pleasure. And this video is all the 3 products after we filter them. All right, so here is product from the acetanilide. And here's the product from the methyl p blah, blah, blah. And here is the product from the methyl benzoate. And back here are the filtrates from each one of those flasks, just so that you can see them and maybe compare them side by side. There's number 2, and there's the filtrate from number 1. All right, folks, so notice at no point in time did I take a measurement of a filter paper. And the reason that I did this is because the mass of the filter paper was not important. I knew that this was not going to be the last step. I knew that we had a recrystallization that we had to do. So with this one, it was almost silly for me to go through and get masses of filter papers, because never did the lab tell me to report a crude percent recovery. It just wants percent recovery at the end of this process, after the recrystallization has been performed. So this is dirty. These crystals are dirty. They're trashy. They're nasty. We need to clean them up. So the way that we'll do that is through the recrystallization process, and that's not yet happened. All right, so here is an observation of product number 1, just a close-up, so that way you can see that a little bit better. Again, make your observations the way that you need to. Here's product number 2. You know, in my opinion, this was had more of a yellow color than the first one, and this almost looked like mushed up egg yolk to me. I mean, that's kind of what it looked like, in like a devil's egg. That's kind of what it was. And then here is product number 3 as a close-up. Notice that this is not fully cream or white from top to bottom. There are little specks of yellow that might be present in those crystals, as you can see. All right, so there's product number 1, number 2, and number 3. All right, so I just let these kind of hang out, and I let them hang out for over a day, and I go back into the lab on the very next day, and the reason I did this is to let them dry, okay? I didn't want to do everything right now, so I left, I went back the next day, and this was on 10/17. So on 10/17, I take the dried product number 1. There we go. That's what the dried product from the acetanilide looks like. That's even more egg yolkish to me than what it looked like the day before. All right, so there's from the acetanilide, and the lab directions are going to tell me to recrystallize. All right, so if I recrystallize this, it says recrystallize from 95% ethanol. Okay, not a big deal. I know how to do this. All right, so here is my product that's dried. I'm going to go get the ethanol jug that we have swimming around in the lab. We always have it out just like a DI water bottle. That's stock. Then I'm going to transfer all of my crystal down into that Erlenmeyer flask. All right, so I have little remnants that are left over, and I'm going to squirt this filter paper with some ethanol to get rid of some of that and put it into that flask. And when I add ethanol, folks, this is what it looks like. So again, you can make your observations the way that you need to. Did it fully dissolve? And the answer is no. Well, I can't recrystallize if it doesn't dissolve. Then it's not called recrystallization. So the object here is for me to add ethanol to get the crystals to dissolve and then allow those crystals to precipitate back out. That is what we're after here, and that is not working for me. All right, so I'll just set this to aside, and I go and get the dried product from number 2. This is the methyl p blah, blah, blah. All right, so there's the dried product in the Erlenmeyer flask. I'm then going to add ethanol to it, and this is what it does. Look at there. That dissolved them much better, but it still did not fully dissolve them. Still not happy with that either. Recrystallization, is not going to take place. So then I go back and I get product number 3. There's what product number 3 looks like. I'm going to add some ethanol to it, and this is what happens. All 3 behave differently with the ethanol additive. This still did not fully dissolve, though. Again, I cannot recrystallize unless I fully dissolve. All right, so here is basically me putting those 3 flasks onto a hot plate. And I'm going to gently warm these up. And I'm going to warm them up because I want these crystals to dissolve. That is what recrystallization is. This one looks like it's already went to that point. This one looks like it's already went to that point. The first one, though, is a little bit more stubborn. So I'm going to continue to slowly warm these 3 flasks until those crystals dissolve, because only until then can we perform recrystallization. So I know recrystallization is going to have to go forward. So I go ahead and get 3 mini beakers, and I put some ice cubes into each one, put a little bit of water into each one to make an ice bath, because recrystallization means precipitate it back out. All right, so after the recrystallization, folks, this is what I see with the very first flask. There is the second flask from my methyl blah, blah, blah. And then this is the methyl benzoate flask. So as you can tell from the flask, I did heat them just enough to get all of those crystals to dissolve for me. And only until then can we really do a recrystallization. I cannot tell you how many times I have to repeat myself, right? And the reason that I repeat myself, folks, is because these are the things that have happened in the lab before. People will read, do a recrystallization from 95% ethanol, and they just squirt ethanol in it and they call it a day. No, that you just added alcohol. That's all that you've done. You've not recrystallized anything. Nothing. Blip. Zero. Nothing. So we've got to make sure that we dissolve it, and then we have to make sure that we precipitate it back out, or allow that crystal to fall back out of solution. All right, so here is recrystallization step number 1. As you can tell, it's already starting to get cloudy again, right? I mean, I see that just by taking it off the heat and just by taking a picture of it and getting my camera set up, it was already coming out. So I'm going to add some cold water, and that forces those crystals back out of solution. And now you can see that there's tons of crystal on the inside. That's what we're after. That is the definition of recrystallization. And now I think that you can fully see the crystals that have formed in that flask at this point. there they are, just in case you need observations for a question. All right, so I'm going to do number 2 the same way. It didn't fully come out of solution immediately. This one was a little bit more stubborn. So there's the flask. It's cool to room temp. I'm going to add some cold, ice cold water. And let's hope for recrystallization. And look at there. The solution's getting cloudy. The solution is starting to change on me. And I'm just going to let this kind of sit out and do its thing. And hopefully I will get crystals from this flask as well, just like I did with the first one. So once more, your observations for the methyl p-Hydroxybenzoate, or the product of the nitration of that reagent, right? And then finally, here is recrystallization number 3 for the methyl benzoate. That's it starting out, getting ready to add some cold water, and you tell me what happens, observations on your bench. Oh, did you see that? Did you see that? Something's happening.
I'm froze.
And that was someone coming into the lab to say that they're froze, just like the Erlenmeyer flask saying it's froze too, with all the cold ice water that I'm making it stay in. Okay, so there's your videos of the recrystallization steps for each one of these. I'm now going to have to refilter because I recrystallized. But this time, the filter paper is important because this will be my final product at this point. So I need to make sure that I am reporting or can report a final volume for each one of these. So this filter paper is labeled with an AC for acetanilide, and I'm going to take the mass of this filter paper, and the mass of the filter paper 0.2063. All right, so here is the solution of the acetanilide. I'm going to pour that through the Buchner funnel yet again, and this is what I end up with. Right there. That's the observation of my recrystallized product for acetanilide. Now I'm going to have to do the same thing for my methyl para-hydroxybenzoic acid. So I take my filter paper that weighs 0.2060. There's my filtrate from that. And that is what my solid looks like. Oh, that's so sad and pitiful. I mean, you compare it to this one, which is the first one, it looks like a substantial amount. And then this one, oh God, I barely had enough to actually go over the holes of the Buchner funnel. So this yield is probably not very good. Is it something that I did, or was it something that the reaction did? Oh, that's for you to tell me. We'll figure it out. So here's just another view of the methyl para blah, blah, blah. So that way you can take a better look at what that product looks like. Do you see the red thing that's here? I don't really know what that was. That just randomly showed up in the flask. I don't know where that little red piece of plastic came from. It was just there. So that's going to stay with the product. Finally, methyl benzoate. I need that filter paper as well. So methyl benzoate filter paper is going to weigh 0.2149. And then as I pour that product through, I'm going to capture that crystal on my filter paper, and that's what I have left. Again, kind of pitiful. I mean, all of that work for that little smudge of stuff right there on the filter flat. Is it me? Am I getting rusty, or is that just the reaction? Who knows? We'll figure that out later. All right, so then I walk away because I'm depressed. I see this little smidgen of product, and then I go back and see that little smidgen of product, and then I go back and see that more substantial amount of product. Okay, well, maybe it's just the reactions. Maybe that's what they do. I don't know, but I go away and I come back on another day. And this is going to be another day, this time the 18th, the day after. The day after, I'm going to go back to my products, and they're all dry, folks, at this point. So this is what the dried, recrystallized product looks like from the nitration of acetanilide. Whoo, that sounded fancy, didn't it? But guess what? That's where we are. This is organic. We're learning this stuff. All right, so this is the dried, recrystallized product from the nitration reaction of the methyl p-Hydroxybenzoate acid. And then this is the observations for the dried recrystallized product from the nitration of the methyl benzoate. So once again, you can make observations of your dried recrystallized product. Now we need masses. Okay, so I go to the balance and I put a watch glass here. This is what I always do because those filter papers have that product, and when I transfer that over to a balance, I don't want my stuff just to swoosh out everywhere. So my watch glass is going to be a little plate for me to scrape that stuff off over on if that is what happens to me. So the tared watch glass, there it is, tared watch glass. And then I'm going to put my filter paper and that product on that watch glass from the acetanilide, and I end up getting 0.6217 grams. So that mass represents the product plus the filter paper. The watch glass has been tared out. That is not included. All right, then I do it again. I take another watch glass, tear it out, and then I transfer my second product over on it. And that gives me a mass of 0.3113. And then I do it again for the third time. There's my tared watch glass. And then I take my product and I put it onto the watch glass. And I get 0.3724. Now, something weird happens here. And what happens here, do you see that filter paper right there? Look at that. It looks like a chunk has been taken out of it. Where did that piece of paper go? I have no clue. Maybe somebody came into the lab while I was gone and just got hungry and took a bite out of a piece of filter paper. I don't know. I have no clue where that little piece of filter paper is went. So this is something that I also want to probably note, because when we go and calculate percent recoveries, this could be something that maybe allowed me to have a lower mass than what we expected. All right, so my job's not yet done. Almost, though, but not yet. I need to do a melting point. So I'll go get my capillaries for the melting point apparatus that we have. And I go back to product number 1, which is here. Look, it just kind of crusted up into one big lumpy mass, right? So I'm going to take this capillary and just cram down onto the inside of it. And then I'm going to do the same thing for product number 2. There's my capillary in the back here. And I'm just going to crunch until I get enough crystal in the capillary tubes. And then I do the same for product number 3. Again, crunch. This was more powdery. It was very easy to load this one up into the capillary tubes compared to the other 2. And then those 3 capillaries are going to go down into my melting point system. And my melting point is right there. Got it turned on. You can see my 3 samples up here at the very top. And folks, we need to go through and we need to create the settings. All right, so here I'm going to push manual method. And I don't really know what these are. So I'm just going to eyeball it, and I'm going to start this thing off at 50 and hit OK. And then the end temperature, it's set at 250. So I'm just going to go to 260. And then I hit OK, and then I'm going to hit start. A warning saying we're going to delete the last one. That's fine. And now if you take a look at this temperature, notice what it's doing. It's jacking all the way up, 28, 29, 30, 31, 32. I mean, that temperature's skyrocketing. It's going to preheat. It's going to preheat till 50, because that's where I told it to start. So you'll hear a little dinner bell ding, ding ding, and that means it's ready to put your cake in the oven, which means we're ready to hit start and start melting our crystal. So it overshot it just a little bit. It's going to bring it back down to 50. And then it will be. And there it was. So now we're going to hit the start button, and now the melting point begins. The melting process begins. All right, so the problem here is that, look at this time, 21 minutes. Based on my temperatures that I have set, my low and the high and the ramp, 21 minutes. I've got better things to do in 21 minutes. I'm going to go back to the lab and I'm going to go clean the glassware that we used together and put it back into the oven. And then I'm going to come back after 21 minutes to see what this system has basically told me happened. I don't need to sit here like a zombie and watch it melt. I mean, that's for people that have nothing else better to do in their life. Me, I'll go clean, I'll go wash, I'll go pick up stuff that I've been using throughout the past couple of days, and then I'll come back to this after 21 minutes is over. All right, so when I do that, this is what I see. What I see is nothing for number 1, nothing for number 2, and then number 3 gives me 254 as a melting point. Bull. I call bull. 1, 2, no melting points. Number 3, that's significantly high, maybe. I just didn't feel good with this report. So what I'm going to do is I'm going to go back and I'm going to re-watch the melting point. And the reason is because the melting point system records the video as it melts. So that way, in that 21 minutes as I was cleaning up, I came back and I see that there was a problem. I can go back and re-watch and fast forward and rewind the video as I need to in order to maybe make my own decision on when this stuff is melting. So that's what we're going to do first. All right, so I'm going to go to this melting point. Right now it's at 137. And I've pointed to this capillary. I'm going to hit play. Now, let's kind of watch this capillary to see when that melts and pick out a temperature at which that happens. You tell me if this is 254 or not. Look at that. There it goes. Look, look. Ta-da! Bye-bye, crystal. No more crystal. And look, now we're at a temperature of 141. So you make your judgment on when you think that crystal has melted, but I guarantee you it's not 254 like the MP50 system told me that it was. No way, no how. All right, so I've got to do the other 2 now. All right, so we're going to look out for the other 2. I'm going to hit the fast forward button. We're going to look at this middle one. That might be the next one that melts. This right now is at a temperature of 154, 155. And you write down the temperature at which you think capillary 2 is going to melt. Still hasn't done it. It's like waiting for paint to dry. Right, so there's the crystals. It looks like they're starting to do something. You record the temperature at which you think it melts. And there it goes. All right, now we're going to be looking at capillary 2 with number 1. Once more, you write down the temperature at which it goes. So I rewound it here just a little bit. And I'm replaying it for you. There's the solid, 204. So the purpose of this melting point is to basically compare that to expected OMP director products to figure out which melting point it closely matches to. And then maybe theoretically explain why we ended up getting the product that we got. So for instance, if this melting point ends up being an O director, why was it an O director? Can we chemically explain why the nitrating group that we added onto the benzene ring went to the O position, or maybe the P position, or maybe the M position? That is the purpose and objective of this lab. And we do that by comparing the melting points with each other. All right? So compare the melting points, figure out whether you have OMP, you know me, and then once you figure that out, does it match theoretical knowledge that you have at this point? And that is the purpose of this lab experiment. All right, folks, so there is 3 labs wrapped up into one. So 3 separate labs you will be turning in, each one a benzene director. The first one is acetanilide and how it directs. The next one is the methyl p-Hydroxybenzoic acid and how it directs. And then the next one is going to be the methyl benzoate and how it directs. Can we theoretically explain why it happens? And can we physically prove that it happened the way that we thought it did, or that it would? All right, so good luck on the labs. Once you turn them in, just start submitting them up and uploading them into Blackboard, and then I'll give you a due date on each one. All right, so keep an eye out onto the course calendar, and until our next virtual lab together, that's it. So easy breezy. Once again, it took me 3 days to do this lab, and it only took you an hour to get the data. Look at that. That's the plus of a virtual world.